Now, it's often the case that, for example, you're given a triangle like this, okay, and I don't know, we might be given the value of the hypotenuse, the opposite side, and then we're asked to find what the angle is, okay? And for the angle, well, we know that there's a relationship between the opposite side and the hypotenuse on a right triangle, and it's through the sine function. So the sine of theta ends up being 3 over 5. Okay? So in other words, theta through the sine function is associated to the value 3/5. Okay? But what we're given is not theta here, it's actually the 3/5, the output. So what we'd like to do is know what input gives me an output of 3/5. So we'd like to reverse the process, and to reverse the process, to associate 3/5 to theta, we'd like to consider what's called the inverse sine function. Okay, we're not ready yet to define that inverse sine function, but we're going to get there. And to get there, I want us to review some properties of inverse functions and what they are. Okay, so recall that the inverse, which you often write f like that, -1 to, it's not 1 over f, but it's just to remind us that it's kind of like 2 to the -1 being the inverse of 2. Okay, so this is where that notation comes from. Remember, it's not an exponent; it's just a notation. F minus 1 is just a symbol on its own. So the inverse f minus 1 of a function f is such that, well, what do we have? Maybe let's look at a diagram. So if I've got x and I apply f, and then, well, I'm going to get f of x if I do that. And if I send f of x through the function f inverse, I'm going to get back to my original x. So that means that if I take f of x and I apply f inverse to it, I get back x for all x. Okay, so if I compose f inverse with f, I'm going to get the function that does nothing, the function that keeps that outputs the same, the outputs the input. Okay, so the input is not going to change. That's what I mean here. Similarly, if I have an output x and I send that through the function f inverse, I'm going to get f inverse of x. And if I apply f to that, okay, I'm going to get back to x. So what does that tell me? It tells me if I calculate f inverse first and apply f to that, so I do f of f inverse of x, I get back x for all x. So those are two equations that my inverse function satisfy. If I've got a point A and apply f to it, I get B. Okay, so that tells me that AB is on the graph of f. Right? If I apply f inverse to B, I get back A. So that means that BA, by flipping around B and A, that is on the graph of the inverse. And because of this, because of these two, it means that the graph of the inverse is obtained by reflecting the graph of f across the line y equals x. Okay, so the graph of f inverse is obtained by reflecting across the line y equals x the graph of f. Okay. So for instance, we've seen with the exponential function that we can get the graph of the log function, its inverse, by just reflecting it. So if I have e to the x which goes through 0, 1, then its inverse will go through, I have to reflect that point here across the line y equals x, it will go through 1, 0. And the graph will look like this. So this is y equals, so this is the inverse of, actually it's ln of x, log n base e. Okay, so each point here is obtained by reflecting it across the line y equals x. You can even reflect the asymptote. If you reflect the asymptote of the exponential function, you get the y-axis. Okay. Also, if I've got a function that sends, I don't know, ABC onto D and E, like that, maybe this is f, function f. Okay, if I want to reverse the direction of the arrows like this, I see that I'm not going to get a function because D is going to be associated to A and B. So this is not a function that's invertible because to D would be associated two different outputs. So that's also because I have two inputs with the same output. Okay, so I won't have an inverse in that case. Okay, and graphically, it means that if I have a function like this, okay, where for the output, I don't know, maybe this output is, this is y equals 3, for example. I have 1, 2, I have 3 x values, x1 and x2 and x3 that have the same y value of 3. And this is not a function that's invertible. So for functions to be invertible, graphically, they have to satisfy the horizontal line test. So a function is invertible if and only if it satisfies the horizontal line test. It satisfies the vertical line test because it's a function, but on top of this, it has to satisfy the horizontal line test. Okay, so if I look at the function f of x equals x squared, for instance, okay, it fails the horizontal line test. Okay, so this is not an invertible function. Okay, however, if I take the same function, okay, but restrict its domain. So let's say restrict the domain to the positive values of x. So now this is f of x equals x squared, where the domain is of f is, I restrict it to the positive values of x. And now it's just this right branch of the parabola. That's the graph of f. Now it's invertible because it satisfies the horizontal line test. Okay, so this one is invertible. Okay, so sometimes you can take a function and restrict its domain in order to get an invertible function. And by the way, if you invert that function, you're going to get, so it's going to go through 1, 1, by the way. So if this is, so let me add, let's say this is y equals x. Okay, 1, 1 stays on the graph, and when you compute the inverse function, you get this function here. And what's that function? It's the function square root. Okay, so the inverse, actually, of f, in this case, when we restrict its domain, is just a square root function. Okay, and that's true when x is a positive number. If you square root it squared, you get back the number itself, no matter what positive number I take. So in other words, the square root function and the squaring function cancel out each other, and I can do it the other way around. If I take the square root and I square it, I get back 2. So this is like doing f inverse of f of 2. This is like doing f of f inverse of 2. And in both cases, I'm supposed to get back x. I'm supposed to get back 2. So more of the story, and that's going to be important for our trig functions, because sine and cosine, because you'll recall that those are not functions that satisfy the horizontal line test. However, we can restrict in our domain to create an inverse function. So we can restrict the domain of a function to make it one-to-one. One-to-one is basically a line function that satisfies the horizontal, whose graph would satisfy the horizontal line test. Okay, so it would satisfy. So to satisfy the horizontal line test, okay, and we can allow it to have an inverse. An inverse function. So this is what we're going to do in the next videos.